All right, so we're now going to start reviewing redox. We're not going to cover everything that was discussed in first year. I'm just going to focus on the stuff that's relevant to aquatic chemistry so that eventually we can have enough knowledge that we can make PE-pH diagrams, which basically are distribution diagrams or speciation diagrams we've done so many times already, but now with PE and pH as our variables of interest. So I want to teach you enough that you can understand those diagrams. And, I've told you all along there were going to be 7 equilibrium constants in this course. And we've done 6 of them so far. KW, KA, KB, KF, KH. Remember we did KH star. It was a bit of a different reaction because we included the reaction with water with CO2, not just the gas solubility. And KSP. So it's 1, 2, 3, 4, 5, 6. So now we have our last one. It's KRed. So we picture now a half reduction reaction. If you remember that from first year, you can talk about oxidation reduction reactions. These are reactions now involving a transfer of an electron. Is either an oxidation half reaction or a reduction half reaction. And the convention is usually to write them as reduction reactions. So we'd have something like this, our oxidized form plus some number of electrons to form our reduced form. And KRed would then be products over reactants, just like always. And we might also have protons or other species for a balanced reaction. It has to be a balanced reaction. All right. So this is what we're going to, the kind of context is we're going to use these equilibrium constants to kind of understand what's happening as we vary the oxidation reduction conditions of a solution. Before we can really get into that, we need to review oxidation numbers. So I'll call those ON, the text that I write below. And we have to have some rules for assigning oxidation numbers, and I want to emphasize these are just specific to this course. These are some simplified set of rules. I'm not going to ask you anything where you need to determine oxidation number. That these rules won't let you figure it out, but they're also the rules that really, in day-to-day life, for me as an aquatic chemist, this is really all I ever have to think about. So the first one, elements have an oxidation number of 0. So anything not combined with anything else is an oxidation number of 0. So that'd be solid copper, oxygen gas, chlorine gas. It doesn't matter if you're not combined with anything other than yourself. There's also elemental sulfur. There's actually 8 sulfurs. Doesn't matter how many. It's not combined with anything that's not sulfur. The oxidation number is 0. And then when you combine in a molecule or ion, the oxidation numbers sum to the charge. So for a molecule, they would sum to 0. So our first kind of sub-rule here is that fluorine is going to have a value of -1. It's the most electronegative element. It really wants electrons. So any compound with a fluorine in it, fluorine itself is going to have an oxidation number of -1. And we can figure out the other oxidation numbers for the constituents based on the rest of the rules. Oxygen has an oxidation number of -2. Again, not oxygen on its own, O2 is going to have a value of 0. And this would not be peroxide. So if you got ozone or hydrogen peroxide or something, you've got different oxidation numbers. But just the normal things, in water and ions, polyatomic ions, it's going to have a value of -2. And hydrogen is going to have a value of +1. And not for metal hydrides. It's actually negative in a metal hydride, but that's not something that comes up a whole lot in aquatic chemistry, so we don't have to worry about it. All right, so let's do some examples. Look at what I set up here. H2O, oxygen's -2, hydrogen +1. So you do 2 times +1 minus 2 equals 0. That's the charge on the molecule, so we're golden. NO3 minus, oxygen is -2. So our nitrogen, well, it's going to be 5, but you can picture -2 times 3 plus whatever, it's got to equal -1. So it'd be -6 plus 5 equals -1. So nitrogen has a value of 5 as its oxidation number. And if we put it in nitric acid, oxygen would still be -2, nitrogen would be +5, and hydrogen would just be +1, exactly what we would expect it to be. And -2 times 3, whoops, I might as well write that down. -2 times 3 plus 5 plus 1. So for our oxygen, nitrogen, hydrogen equals 0. All right. And we do another nitrogen species. We can talk about ammonium. And we'll do ammonium. So we go hydrogen, the value of +1. So we got +1 times 4 plus something is equal to +1. So our something has to equal -3. So nitrogen's -3. And you can say nitrogen in ammonia is reduced compared to nitrogen in nitrate. All right, so it won't be any more complicated than that. That's the type of thing you'll have to be able to do with oxidation numbers, just determine what's oxidized and what's reduced. Now the same as all our other log K values in this class, they're determined experimentally. We're going to look them up from tables. In first year, you looked at reduction half reaction potentials. It's a half reaction because you're going to see as we go forward that we talk about an oxidation half reaction and a reduction half reaction. You combine the two to get an overall redox reaction. Anyway, you're used to in first year half reaction potentials, and you can see I found a website here. Here's what they would look like, standard half reduction potentials. I'll put this website into my notes. Like this. You'll have to cut and paste this because I don't know how to add it as a hyperlink. Okay. But here, use log K tables instead. It's the same information. We could write the equation that shows how reduction potential is related to the equilibrium constant, K red. But I'm never going to ask you to convert back and forth. We're going to do all of our quantitative questions in terms of tables of log K values. So I looked up a website that shows that. So you can see here the table right there. So there's I can't circle, I was going to circle it, but there's all the log K values as the first numerical column there. All right, so I'll paste this in. All right, so you can just look at those, just give yourself an idea of what the half reactions would look like. I'm obviously going to give you the half reactions and the log K values on the tests. For both ways of representing half reduction reactions, we compare to standard hydrogen electrode. Standard hydrogen electrode. And so that's given a value of 0 in terms of potential, or a logKred of 0, the corresponding reaction, and you can look for it in both of those tables, is like this, where we take +1 oxidation number and we go to 0 oxidation number, and that's why it's called reduction. So we've taken a number and we've gone lower. The opposite direction, if the number gets higher, the oxidation number gets higher, we call it oxidation. And so the K for this reaction is the partial pressure raised to the stoichiometric coefficient divided by the hydrogen ion concentration and the electron, and it has a value of 1, and log K red has a value of 0. And this is just by definition. I won't go into why it is, but we can't actually measure potentials. We can only measure potential differences, so we have to compare to something. And so this is the reaction that was decided to be what everything else is compared to, so it was set to have a value of 0. All right, so that's enough background stuff. We're going to talk about the important redox reactions in natural waters. It's the redox ladder that we call it. And I'm going to talk about PE pH diagrams. So I'm going to make 2 more sets of notes. All right, thank you.